The last topic we'll cover in section 4.4 is the second derivative test. This is theorem 4.9. Let f be a function such that f prime of c is equal to 0, and the second derivative of f exists on an open interval containing c. If the second derivative is positive at c, then f has a relative minimum at c comma f of c. If f double prime of c is less than 0, then f has a relative maximum at c comma f of c. It's also possible that if f double prime of c is equal to 0, then the test would actually fail, and we wouldn't be able to know immediately whether f has a relative min, max, or neither at the point c, in which case we'd have to resort back to doing the first derivative test by making a sign chart. One of the ways and images I've always seen people kind of describe this that might help you to memorize the second derivative test is if you think of the second derivative as being greater than 0. So if the second derivative is greater than 0, then the graph would be concave up. So think of the second derivative as positive. So it's greater than 0, so it's positive. So think of like a happy face. And if you had a happy face, the mouth would make like a concave up, which would provide a minimum value. On the other hand, if the second derivative was less than 0, then if it's negative, if you think of negative things, that'd be like a frowny face, and that would produce a maximum. So maybe this will help you to memorize the second derivative test. Let's take a look at example 4. We were asked to find the relative extrema of f of x equals negative 3x to the fifth plus 5x cubed. Anytime we want to find extrema, it's going to begin by finding the critical numbers. Let's find the derivative. F prime of x would be equal to negative 15x to the fourth plus 15x squared. For our critical numbers, let's go ahead and set the derivative equal to 0 first. That is, where is negative 15x to the fourth plus 15x squared equal to 0? We can pull out a GCF of negative 15x squared. That'll leave us with x squared minus 1 equals to 0. This factors more because we have a difference of squares. This will factor as x minus 1 times x plus 1 equals to 0. Set each factor equal to 0. And we get 3 critical numbers. This one will produce x equals to 0. This one will produce x equals to 1. And this one will produce x equals to negative 1. There won't be any places where f prime is undefined. F prime is a polynomial, so it's going to be defined everywhere. So all total we get 3 critical numbers. Let's now use the second derivative test to classify each of those critical numbers. F double prime of x would be equal to negative 60x cubed plus 30x. If I plug in x equals to 0, it turns out that f double prime of 0, if you work it out, that's going to be equal to 0, which means that the test would fail. So we don't know immediately whether or not at x equals to 0, whether we're going to have a relative max or a relative min. Let's come back to that one in a moment. If we look at x equals to 1, if I plug this into the second derivative, f double prime of 1 would be equal to negative 60 times 1 cubed plus 30 times 1, which would work out to be negative 30. So at that critical number, the second derivative is negative. And remember, if the second derivative is negative, then that means we're going to have a relative max at x equals to 1. We can go ahead and find that value by plugging it into the function. The value of that relative maximum, f of 1, would be negative 3 times 1 to the 5th plus 5 times 1 cubed, which would be equal to positive 2. So we have a relative maximum of 2 at x equals to 1. Let's see what's going to happen with negative 1. If I look at f double prime of negative 1, this would be equal to negative 60 times negative 1 cubed plus 30 times negative 1. And this would be equal to positive 30, which is greater than 0. If the second derivative is positive at a critical number, then that's going to be a relative min. So we have a relative min at x equals to negative 1. If you want the value of that relative min, then you need to take negative 1 and stick it into the function. I'll let you do that on your own, but if you evaluate f of negative 1, this is going to be positive 3 minus 5 would be negative 2. And now we just have that one unclassified critical number, which was x equals to 0. Whenever the second derivative test fails, we can always go back and use the first derivative test. So let me kind of come back here. My critical numbers were negative 1, 0, and 1. And we need to see what is the sign of the derivative on either side of 0. So even though I have 4 regions here, I'm not going to do the complete sign test. I just need to see the sign on either side of 0. So I need to know what is the sign of f prime in region 2 and region 3. In region 2, you could use the test point x equals negative 1/2. F prime of negative 1/2 is going to be negative 15 times negative 1/2 to the 4th plus 15 times negative 1/2 squared. This is going to be equal to negative 15 sixteenths plus 15 fourths. And if you go ahead and get common denominators, you'll find and see that this value is going to be positive. So to the left of 0, f prime is positive, which means that the function is increasing to the left of 0. Let's pick a test point in, let's say, region 3. We can use x equals a positive 1/2 in that region. If we plug a positive 1/2 into this, we actually are going to end up getting the same value. It's going to be negative 15 over 16 plus 15 over 4, which will also be a positive value. So it's going to be increasing to the right of 0 as well. So at 0, the graph was increasing. It's momentarily going to have a derivative of 0, so it kind of halts a moment at 0, but then it continues to increase. Because the first derivative does not change sign at 0, we get neither a max or a min. So at x equals to 0, there is neither a max nor a min.